The topic of this course is digital speech signal processing. We will focus on the digital speech signal, that is to say, the discrete time signal, which can be received and processed in computer and some devices. My name is Wang Jing. I am Associate Professor in School of Information and Electronics, Beijing Institute of Technology. This course aims to enhance the students' ability of using basic theory to solve practical problems. Through this course, students can master the basic theory of digital speech signal processing, mathematical analysis and modeling methods of sound objects, meanwhile understand the specific application and cutting-edge technology in the field of speech processing. Before the class, some prerequisite courses are needed, including signal and system and digital signal processing. Here are some knowledge points used in this course. The first one is how to convert continuous time signal into discrete time signal. The second one is how to express the discrete time system. Here is a short video about the Z transform, which can be used to describe the discrete time function.
So hopefully you recognize this. It's what I said would show up later. This is the actual arithmetic of the moving average, summing two samples and dividing by 2. So the arithmetic we perform on the samples shown on the right, and the equation that told us the distance from the zeros and poles here on the left, along with the corresponding plot, are directly linked by something called the Z transform. For those that know what the Laplace transform is, this is the discrete version. Now we can more quickly see what other kinds of sampling will do. Like if I want to do a moving average with 4 samples at a time, then the arithmetic would be this here, summing 4 neighboring samples and dividing by 4. Now doing the same thing backwards will change the x and y of n to x and y of z. When there's a -1, the z transform makes it z to the -1 x of z. Then -2 and -3 do the same thing with those corresponding exponents. Then since there's an x of z in every term, I can divide that out. And lastly, I'm just going to remove the negative exponents by multiplying by z cubed to top and bottom. This is the function that tells us everything we need to know. The zeros are -1, I, and -I, those are what make the numerator 0, and the poles are only at z equals 0, the origin. So I'll put those on our unit circle plot from before. The plus or minus I do go on the y-axis, as that's really the imaginary axis when dealing with pole 0 plots. Then for any sampling interval denoted by the angle, if I multiply all the distances from the zeros, then divide by the distances from any poles, and also divide by 4 because it was there in the denominator, that will tell me the output amplitude of the reconstructed signal for a 4-sample moving average. This 0 here at pi over 2 means as we slide towards that, the output amplitude also goes to 0, which we can see here since the average of any 4 neighboring samples now is 0. Now I've been using one sinusoid this entire time of one specific frequency, but that's really all we need in order to analyze any signal.
The next question is, do you know Nyquist sampling theory? The signal transforms from time domain to another domain are very useful, such as DFT, discrete Fourier transform, wavelet transform, and other possible methods. Here is a short video about the concept of DFT, which is often used in speech signal processing.
So we can get various types of signals through sampling, but once we have that information, how can we translate it into data that we're going to analyze, change, or recreate? That's where the Fourier transform comes in. There was a French mathematician named Joseph Fourier who had this crazy idea that a complex waveform, it could be light, heat, or sound, can be essentially broken down into its component parts, which is just a group of simple sine waves. And this is the equation that he came up with to do that. It's called the discrete Fourier transform. Essentially, the discrete Fourier transform is a mapping of data between two domains. We take input in the time domain, and we get output in the frequency domain. We use zero-based indexing, where you can see lowercase n starts at 0, and we're summing up until n minus 1. X sub n represents the nth element of the input, and x sub k represents the kth element of the output. Lowercase x denotes our time signal, uppercase x is our frequency signal, and the signal level at frequency k is just equal to the sum of the signal level at each time n multiplied by that complex exponential that you see on the right.
How to design and use some digital signal filters, such as FIR and IIR. If you forgot such kind of basic signal processing knowledge, you should review the prerequisite courses before you learn this class. Here is a short video to show how to filter a signal with MATLAB program.
A filter is a system that operates on a signal to reduce or enhance certain properties. Digital filters are widely used in multimedia, biomedical engineering, electronics, communications, and many other areas. In this video, we will see how you can design and analyze digital filters and apply it to a signal. I will provide answers to following two practical questions. How can I remove an unwanted tone from a signal? And how can I compensate for the delay introduced by a filter? Let me show you how you can remove an unwanted tone from a signal. A tone is a signal that rings only at one frequency. Let us load a signal into MATLAB. The signal is a series of voltage readings corrupted by noise. Often it is hard to tell anything about the nature of the noise just by looking at the signal as a function of time. We can visualize the power of the signal across different frequencies by using the function periodogram. You can see a peak around 60 Hz in a plot. This peak is likely caused due to the presence of 60 Hz power lines interference, which corrupts electrical signal measurements. We can use a bandstop filter to remove the 60 Hz interference. A bandstop filter with a narrow stop band eliminates a tone of particular frequency. We can use the design field function to design the bandstop filter. We specify the stop band to be in the 59 to 61 Hz range. We can analyze the filter response using the FVTool command. The next step is to filter the data using the filter command. Let us plot the power spectral density of the filtered signal. We can clearly see that the bandstop filter has removed the 60 Hz noise. In this way, you can use a filter to remove an unwanted tone. We just saw how to use a filter to remove an unwanted tone from a signal.
The main content of this course includes 12 chapters. Firstly, we will have a brief introduction of the speech processing applications, the history of speech signal processing, and the basic knowledge of speech signals. Then we will introduce the fundamentals of speech processing, mainly including two important techniques: short-time analysis and pitch estimation. The content of Chapter 3 is very important in digital speech signal processing. That is, speech production and perception model, corresponding to human speaking and listening procedure respectively. Chapter 4 to 7 will introduce some key techniques of speech processing, such as linear predictive analysis technology, homomorphic analysis, vector quantization, and hidden Markov model. Chapter 8 to 11 will introduce the most useful speech processing technologies: speech coding, speech recognition, speech synthesis, and speech enhancement. Finally, we will have a brief introduction of the latest development in speech signal processing, especially the hot technique deep learning since the year of 2012. For example, deep learning-based speech recognition and speech separation techniques. There are some reference books that the students could consult in this course. You could also find a lot of papers researching on different topics in speech processing online. That's all for this session. See you next session.